Hello everyone, I'm Zhang and a Lantern Community Ambassador. Today we continue our series of courses on building agent-take RAG applications based on LangChain and OceanBase. This video is the second installment in this series. Today we'll mainly introduce the basics and architecture of RAG applications. Before diving into the specific course content, let's first give you a quick introduction to the course's dedicated website. We'll put the website address in the video description and comments section for everyone to access. As you can see, on this website, we'll upload the slides from each session for everyone to browse. For each set of slides, we also provide both English and Chinese versions, and you can switch between them using the controls at the bottom of the page. You can switch the language there. For our video explanations, we'll use the English version to ensure the accuracy of the relevant terminology. Later on, we'll also upload downloadable course materials and resources to this website for everyone to use. Now, let's move on to the content of this session. This course is also jointly produced by OceanBase and the LangChain community. You're welcome to follow my social media for more detailed information about the course. In this session, we'll introduce three main topics. First, we'll cover some basic concepts about RAG. Next, we'll show you how to build a simple knowledge base with the core supported by a vector database. Finally, we'll introduce two fundamental yet practical RAG implementation models, the traditional RAG system and the agent RAG. Next, let's talk about some basic concepts of RAG. At its core, RAG is really about context management. So what is RAG? Literally, it stands for retrieval-augmented generation, content generation enhanced by retrieval. So its core is still content generation. The main body responsible for content generation is the large language model. RAG addresses some issues that arise when large models generate content independently. For example, as everyone knows, the knowledge structure of large models is limited. Also, although it can supplement additional information through the context window, the size of the context window is fixed as well. It's impossible to just dump a huge amount of data in at once and expect it to answer. So how do we address this issue? RAG addresses this by using a filtering and selection process. It first retrieves information that is relatively useful, practical, and valuable, then fills the context window with this data. Moreover, this data can be tracked and has clear, citable sources. Then, by supplementing the context window with effective information in this way, it ultimately improves the accuracy and effectiveness of the final response. This is how the system is built. So in the end, RAG allows you to construct a system based on the internal knowledge of large models. And then, by combining with high-quality external knowledge, you get a knowledge system that is both traceable and based on external sources. Now, the basic pipeline of RAG itself is actually quite simple and straightforward, but keep in mind that this is just a foundational process. As we can see from this flowchart, after a user submits a question, we perform a data retrieval from the vector database to find the most relevant documents. Then, we combine the user's question with the information from these retrieved documents and feed them together into a large language model, which then generates an answer. This is the most classic RAG workflow, but it doesn't mean that all workflows are like this. We'll see some other architectures later on. So within the context window of the large language model, a knowledge structure like this is generally formed. First, it will include system information, then our context. Here, the context usually also contains some traceable metadata about the content. In addition, there's the user's question and possibly some execution examples as well. By combining all this information, the large language model generates content, which tends to be relatively effective. In addition to the basic pipeline structure we just saw, actually within the RAG architecture system that we often use nowadays, there are several different forms. We've roughly organized three main types for everyone. The first type is called two-step RAG, which is the most basic two-step process we saw earlier. First, retrieve relevant document information, retrieve similar groups and recall related information, and then generate based on this information. This is the most controllable and the results are relatively predictable since there are only two steps. However, its drawback is that no matter what the question is, it will always perform a recall, which can often waste resources. To address this issue, we have developed agent RAG. This is also the most common form in use today. Here, an agent tries the process, first determining whether a recall or retrieval is necessary. If retrieval is needed, it can perform multiple rounds of retrieval and use different tools and methods for searching and recalling information. As we saw earlier, we can use our order database or we can use a traditional database. Even document databases and the like can all serve as tools, with the agent making the choice and decision on which to use. Whether to perform multi-turn or single-turn operations is also entirely up to the agent to decide. So its flexibility is extremely high, and it can also carry out multi-turn reasoning and inference. However, the potential issue is that it might be more time-consuming, right? In scenarios that require quick responses, this kind of rack system isn't particularly advantageous, but what it emphasizes is greater completeness and more flexibility. But flexibility doesn't necessarily guarantee a better final result, because even in multi-turn loops, you might still end up with recalled and retrieved data that isn't of very high quality. To address this issue, another system has been developed, which we call the reflective or corrective RAG. This approach places greater emphasis on the entire execution chain of RAG, where we need to pay more attention to performing a reevaluation. This could be a data validation or a kind of self-reflection. Reflection means we need to determine whether the data we've retrieved or the steps we've executed in the process are accurate and effective. Only when we have qualified data can we finally pass it to the large model for generation. After the generation is complete, we then continue to perform some calibration to ensure that the result actually answers the question, has a certain degree of accuracy, and can truly and effectively reflect the real situation. If not, we have to go back to the very beginning to re-ask the question, rewrite the question, or perform retrieval and recall again. So it's a system that loops repeatedly and includes many decision points, this kind of reg system. It has self-correcting capabilities and also self-validation abilities. It's more complex, but it ensures better quality. So in our daily work, we actually use all three types. For simple and predictable cases, we might just use the most basic two-step rack. Then, by using the agent rack, we can better control the overall process and make it more autonomous and self-driven. For scenarios that require higher precision, on the basis of agentic reg, we add more glyphs and more in-the-loop validations to improve the overall answer quality of RAG. Alright, and the next section will introduce how to build a knowledge base. Because before we can do retrieval and recall, we definitely need a source to operate on. So building a knowledge base is actually the foundation for the RAG system. In fact, it can be divided into dynamic and static types. A knowledge base doesn't always have to be built in advance. But we can also obtain information through many dynamic methods, which is also a type of knowledge base in a certain sense. However, we won't focus on that in our explanation. We'll mainly introduce preset knowledge bases. So when building this kind of preset knowledge base, there's usually a classic pipeline, which involves four core elements. The first is documents. The document loader, or the document loading tool, is responsible for obtaining document information from various sources. Of course, when we talk about documents here, we mean it in a broad sense, any kind of information. In fact, all kinds of multimedia text information can be considered as document information. So after obtaining this kind of information, we then do a preliminary compilation of the materials. That's the first step. The second step is, once we have this large amount of data, we need to split it into chunks and store it in a vector database or in our subsequent databases. Why do we need to split it into chunks? Mainly because if you don't and you try to put the entire content into the database, on one hand, it's hard to store and might overflow, and on the other hand, when you're retrieving it, if you put everything in at once and retrieve it all at once, it's no different from just feeding the entire thing to a large model. It'll also overflow, and you still won't get accurate or relevant data chunks related to your question. So in most cases, we need to do some trimming, and the extent of this trimming actually depends on the content itself. So some adjustments are needed. This means that the number isn't a fixed value for the size of each chunk. There might be different ways to slice the content. The third step is to store it in a vector database or a specific storage system. For vector storage, the first thing we need is to vectorize the text, or in other words, vectorize the document content. But keep in mind, vectorization here doesn't just refer to documents or text. It can also include images. Audio and video can also potentially be vectorized. So after everything is finally converted into vectors, They're stored in a certain vector database. If your storage is in a vector database, then you might need to use some other pre-processing methods to store them. Ultimately, the goal is to store and search the data. For vectorized data, it's the vector database that supports these operations. So this forms a rather straightforward, you could say a 3 or 4 step single link pipeline for building a knowledge base. This workflow is basically the most fundamental one. In real world scenarios, we actually see a lot of variations, but here I'm introducing the most basic workflow to everyone first. Next, we've actually prepared an example for everyone. It's a 10K report from Nike. You can download it using the link above, and you can practice with this document locally on your own. Now, let's also show everyone a general overview of the current data situation, including the total file size, the storage size after vectorization, the vector model we used, the chunking method, the chunk size, the overlap, and finally, the total number of chunks we generated. Next, we'll give you a general idea of how we ask questions, and then in the following slides, we'll go into more detail step by step. We'll show you examples for each stage of the pipeline we mentioned earlier, demonstrating how we process the document at each step. Alright, so first, the initial step is still loading the document. Using the link above, you can access a series of document loaders from LangChain. Note that document here is used in a broad sense. We have different ways to load data from various data sources, and ultimately, the loaded data will become a collection of document objects. In this example, we're showing you how to use a PDF loader, which allows us to directly read a file, in this case, the Nike 10K PDF file. After reading it, you'll see that we generate an array of documents, and then you can access the contents inside. Each document has its own content, called page content, as well as its metadata. This includes which file it comes from and which page it is. Every page will have this kind of data, preserving both pieces of information, which helps describe all the slices of content in your document. Alright, and then, besides this, the LangChain ecosystem also provides a wide variety of different types of document loaders. For example, there are web loaders that let you directly fetch a document from the internet or even an entire directory, allowing you to recursively retrieve documents. For example, you can load all the files from an entire GitHub repository, or you can fetch local markdown files. You can also access online files from Google Drive. Basically, all kinds of data sources are supported. You can learn more by checking out the link above, so I won't go into further detail here. The second step is document chunking, and there are also many different ways to do this. Here, we recommend using the classic recursive character text splitter for chunking. It's one of the most commonly used splitters, because this method is suitable for most scenarios. However, I want to especially point out that in many cases, such as in the programming field, if we're building this kind of database, using this chunking method isn't really appropriate. That's because there are a lot of code snippets and a lot of markdown documents in this domain. In these cases, we need to use specific chunkers that can recognize code blocks and handle markdown documents more effectively. Otherwise, the biggest problem that can arise is your code might get split in half, and when you retrieve it, it's incorrect and incomplete. The recursive character text splitter is a relatively useful chunker. Its core concepts include the idea of a separator and a chunk size. So the trunk size defines how many characters are in each chunk, in each slice. The way the text is split is determined by the separator. For example, here it will recursively split and it will follow this order. First, it splits by new lines. There are empty lines, then lines with new lines, then periods, and then spaces. And the last one, make sure you always include this one, represents text, meaning each character can be split individually. You must remember this. The way it slices is to first split according to the separator, which might break the text into several large chunks. Then, for each chunk, it checks whether it exceeds the trunk size. If it does, it will further split it. At the same time, it will ensure there is a certain amount of overlap between the front and back. I won't go into too much detail here, but I recommend everyone start by trying out this recursive character text splitter. If you haven't used these text splitters in LangChain yet, this is a good place to begin. Alright, so it also provides a lot of other slicing methods, including slicing directly based on the size of your text or by token size. What's shown here is slicing by text, but you can also slice entirely based on token length. You can also slice based on text structure. For example, as mentioned earlier, we can slice by code blocks, by markdown sections. These are all very commonly used methods now. Slicing by HTML structure is also very common. These are all widely used slicing techniques. All right, moving up, we have vectorization. Here, in this example, we will use vectors and we'll be using Silicon Flow, an online service for silicon-based flow. So in this case, we'll also make use of some other third-party tools. Okay, after we've loaded the vectors, the key point here is that you can directly use our LangChain embedding model to perform embedded queries. You can pass in a text string and convert it into a vector. You can also use this to convert a whole series of documents as well. All these methods are provided by LangChain. It wraps these different vectorization models into an embedding model for you to use. All right, so here's something you need to pay special attention to. We have different vector models, and their dimensions, the dimensionality of their data space, are not the same. This is something you really need to watch out for. Also, when it comes to the distance between vectors, if we want to get their similarity, there are different ways to estimate that similarity or distance. Whether we use cosine similarity or some other estimation methods, we need to be mindful of these as well. Pay attention to this. Here, I also want to specially recommend a third-party tool we use in this context, which was created by teacher Typing from our community. It's called Legend That You Tales, an installation package of Python toolkit like this. It offers a wide range of processing models, as well as a series of methods for handling things like our own message history, and includes middleware for LianQuanV, along with many additional supporting tools. So in this regard, in this example, we mainly use two parts. One is to first register an embedding provider, because in the LangChain ecosystem, the main model providers it supports are mostly overseas vendors, and the support for domestic providers is not very strong. So by using this method, we can quickly bind our provider's URL and associate it with a specific prefix. This way, we can very conveniently, just like we saw earlier with Silicon Flow, then a colon and then a model name, use this format to quickly load your model. Second, after we've registered, the way we load these models is called load embedding. With these two functions, we can easily register domestic models and quickly use string-based descriptions to call these model providers, as well as the models offered on their platforms. Similarly, there will also be a two-part registration method for chat models. We'll see this later on in the practical examples, so you'll be able to see it in action. All right, the final step is vector storage. When it comes to vector storage, we're excited to introduce OceanBase's vector storage capabilities. OceanBase itself is actually a database with hybrid storage capabilities. Vector storage is just one part of its capabilities. It also supports traditional structured data storage as well as full-text search capabilities. So for us, if we want to handle digital storage, it's an all-in-one choice. It's a really convenient way to store data. We don't have to choose multiple databases and then configure them separately. With just one database, we can solve a lot of problems. Of course, what we're showing everyone here right now mainly focuses on its vector storage capabilities. Here, we can configure the vectorization model up front, then set up the table and connection parameters, and also configure our matching method. Finally, after setting up the indexing method, you can start using the vector storage. All right, once we have the storage set up, we can add all the document chunks we prepared earlier into it. As we add them, these chunks will be vectorized and then stored. This whole process is encapsulated in a method. The vector store encapsulation is actually a series of methods, and OceanBase currently implements this encapsulation, so you can directly use the corresponding utility functions for vector storage. To quickly import data like this, you can also use its corresponding search function, similarity search, to perform similarity matching and retrieval. All right, so the key point here is we need to pay attention that these indexes are all configurable, but of course, this depends on the underlying database used for your vector storage. Not all of them support these indexing methods. At the same time, whether these databases can support some hybrid searches, for example, being able to do both sparse and dense retrieval and indexing, this is also related to the database itself. So the content listed here is actually all. These are some retrieval and indexing methods that OceanBase currently supports natively, so everyone can get a preliminary understanding. Now, if you want to integrate OceanBase with LangChain, you absolutely need to use a component of OceanBase called LangChain OceanBase. You can also learn more about it through this link. What it does is wrap OceanBase into the LangChain vector store for everyone to use. This way, you can use the standard LangChain vector store approach to build indexes for your content and perform similarity searches. So you don't need to spend extra effort maintaining your own wrapper. You can just follow this project, which will continue to be updated and improved. Later, we'll also see how to use this wrapper to perform hybrid search. All right, so finally, let me give you a brief summary. We've now established a complete pipeline for building the knowledge base, and we've listed it out here for you. Throughout the entire process, we've used certain components, and overall, we'll be relying on the open source ecosystem to provide this for everyone. Basically, we have the foundational support for document generation and chunking. Then, we'll make use of third-party tools to help everyone quickly import domestic vectorization models. For vector storage, we'll be using OceanBase, which is a hybrid solution. It's an all-in-one data storage solution, and we'll also use its components. With LangChain and OceanBase, you can quickly integrate it with LangChain, and in the end, you'll have a complete pipeline. So by using these tools, you can actually build a knowledge base very quickly. So we've prepared a dedicated notebook for everyone, which will fully demonstrate how to use these tools to organize and prepare a knowledge base. All the detailed code and execution results can be found in this notebook. You can get a complete understanding. Once you receive these materials, you'll be able to conduct more detailed experiments and obtain more information. Alright, finally, let me introduce some RAG modes to everyone. In this session, we'll only cover the most traditional two-step RAG and agent RAG. In future videos, we'll introduce more complex hybrid RAG and reflective RAG. Alright, so for the two-step RAG, we've actually already seen a similar flowchart earlier. When we translate this into code, it's also very simple. The first step is to use the vector store we mentioned before, and then use its function called as_retriever to convert it into a retrieval object. Now, the retrieval object is actually a fairly broad concept. Its core function is that you can give it an input and it will return an output to you. It can do this either through retrieval or web search methods. Both are possible. It's an abstract object. Once we have retrieval, we can use language here to build a call chain, because two-step retrieval is a classic two-step process, and it's a very straightforward kind of call. A chain is just a chain, so for its input, we use the retriever to perform document retrieval. The results we get are then concatenated into a single document data column, a long piece of data. We concatenate the long text data like this and then use it as context. Combined with the user's question, which we mentioned earlier, this forms a complete input that gets filled into the system prompt, specifically into the prompt template. Of course, this template may also include the system prompt and some other examples as we discussed before. Finally, we pass this complete content to our conversational model and then it can execute. The final execution call is simply a straightforward file-based conversation. There's nothing special about how the model is called. So the core is that we use a vector store, turn it into a retriever, and then we can perform content retrieval. That's the main point. The core is this retrieval object. Alright, so its advantage is that it's pretty straightforward and simple, making it quite predictable for lightweight scenarios, but its drawbacks are also very obvious. It can't distinguish between simple and complex questions, treating them all the same, and there's no way to verify the quality of the results. So in this kind of two-step RAG architecture, we actually use it relatively rarely nowadays. It's only used in some very specific and fixed scenarios. As you can see from its example, the process is extremely straightforward. Once a question comes in, it will definitely help you search for some related content no matter what. But this content might have no actual relevance to your question because it just matches the two most similar items based on similarity scores. Even if the matching result is quite low, although you can do some filtering still. Relatively speaking, this matching step is always executed and then you get the result. The agent, Greg, on the other hand, is relatively more effective and a bit more advanced. That's actually a scenario we currently recommend to everyone and find quite practical. Alright, so the core idea here is what we introduced in the previous video. First, we need to build a tool. The tool we're showing you here still uses a vector store for similarity search, right? You can also use it by converting it into a retriever to perform retrieval and recall. That works too. But the key point is that you must first build the tool. The second step is much simpler. We just use the create agent method, which we introduced in the previous video. Just put the tool in, set up some system prompts, and then pair it with your conversational model to execute. As for the example of the conversational model, we'll also provide a dedicated notebook for you later so you can access it directly and learn how to use it. Once you create it, you can execute this agent to carry out a task. The internal process is entirely determined by the agent itself. It decides whether it needs to execute and call your tool. The advantage of the whole agent setup is that it's flexible and controllable, supports multi-step reasoning, and allows the agent to fully utilize its powerful reasoning and decision-making abilities. At the same time, with version-based agents, we can mount a wide variety of middleware to finely control and enhance the capabilities of the entire workflow. Its drawback is that it can be relatively time-consuming, and if you don't use a good framework and debugging tools, the controllability of the whole process will decrease. Also, since its core is tool invocation, it requires us to have a solid foundation for tool calling capabilities and to support models with good performance. Otherwise, there will be significant issues. For this approach, in scenarios involving simple problems, it may not call any tools at all and will just answer directly, relying on the model's own knowledge. And only for more complex problems will it start selecting tools. Here, I want to emphasize again that later, when we talk about hybrid search, you'll see that we provide it with different tools, allowing it to choose among various data sources. For example, if it thinks a question is better suited for vector search or for full text search, it can make its own choice. All of these decisions are made autonomously by the agent. And regulation, so its adaptability and flexibility are much higher. Okay, so if we make a simple comparison between these two modes, we can basically see that although each has its own advantages and disadvantages in terms of controllability, flexibility, and latency, in most of our current application scenarios, it's generally better to choose the agent approach first. Overall, it offers higher flexibility and autonomy unless your current model performance is quite poor, or if your scenario is really straightforward. In that case, you can still fall back to using the two-step RAG approach. Alright, as mentioned earlier, we've provided you with two additional notebooks. One is for implementing the two-step RAG method, and it contains a complete example showing how to load the dialogue model, the vector model, and how to implement the process. In addition, there's also an agent. This RAG implementation is also very comprehensive. The notebook includes the execution process and the final results, so you can use these two notebooks to further explore and understand the content. Alright, so to wrap up, let's summarize the core content of today's presentation. First of all, the essence of RAG is context engineering. It's about managing context. Ultimately, it serves to help large language models overcome their limitations in terms of knowledge. To achieve effective data recall and retrieval, the foundation is to first build a knowledge base. There are relatively standardized methods for constructing such a knowledge base. You can leverage platforms like LangChain ecosystem or environments with strong data support like OceanBase. This allows for rapid construction, after which you can gradually optimize it. I recommend building first and then optimizing as the best approach. So when it comes to different RAGs, there are actually various RAG architectural systems, including the most basic two-step RAG, agent take RAG, and reflective RAG. Today, we'll mainly introduce the first two types, and later on, we'll provide more details on how to build hybrid and reflected RAGs. Finally, in today's video, we've actually provided a lot of examples for you. You can use our embedded notebook to further study and understand the content. That's about it for today's session. You can scan the two QR codes below to learn more about LangChain and OceanBase. And we also welcome you to follow our upcoming videos to learn about how to build hybrid and reflective RAGs. So that's all for today's session on risks. Thank you, everyone.